Hi, everyone. Welcome to Not a Chat App. My name is Derek. I'm a software engineer at ThousandEyes. And today, I'm going to talk to you about how we use WebSockets to make our systems fully reactive. So full disclosure, it's my first time doing a meetup, so I'm a little bit nervous. That's why I have the flashcards, because I'm old school. But yeah, please go easy on me. So I wanted to talk about this topic because I feel like a lot of the things we see on the internet today about WebSockets and like reactive programming generally cover use cases like consuming stuff from a Twitter feed or like chat applications. And it's obviously not the type of use cases that our companies or our businesses are in. And they don't necessarily address things that you see in real-life systems and real-world engineering problems. So my goal for the next 30 minutes is to give you an overview of what being reactive means for us, show you some code for what reactive programming looks like at ThousandEyes, and give you an overview of like the lessons that we've learned along the way. But before we go any further, I want to first define what reactive programming means in the context of this presentation, because I feel like there are a lot of definitions out there. The term is a little bit conflated. The term is a little bit conflated, but for the context of this presentation, I'm going to say reactive programming is programming with asynchronous data streams. So this is, like in the talk previously, the asynchronous data stream could be the bytes coming out of a database. It could be clickstream. It could be user input, so someone typing into a keyboard. For us, it's the events on a message queue. But asynchronous data streams can be anything. And I think this concept will be a little bit clearer when I show you some code. So for today, I first want to give you a quick overview of ThousandEyes and the specific team that I work in. Then I'm going to take you through our architecture, show you some code, and finally some lessons learned going through all of this. Now, ThousandEyes is a software as a service company. Our main aim is to help our customers gain visibility into the internet. And our customers are mainly enterprises, and I'll kind of go into a little bit more detail about what this means later. But within ThousandEyes, there are multiple product teams, and I sit within one of these product teams. And our product team is called the Endpoint Agent. The Endpoint Agent is a piece of software that our customers can install on their computers or on their employees' laptops to gain a better understanding of their employees' experience with the internet applications that their employees use. So to give an example, if you're a company that's using Jira and you're using the cloud-hosted version of Jira, then our software can help you figure out if your employees have issues connecting to Jira. It'll give you metrics to diagnose the problems. So concretely, the Endpoint Agent is a C++ piece of software that we install into the employee's laptop. It gathers data and various metrics, which it then sends to our backend. And then we also have a web application that kind of makes this stuff pretty and shows it on graphs and stuff. Now, to kind of explain how reactive programming is involved, I want to explain a feature that our product supports, which we call scheduled tests. And scheduled tests effectively allow our customers to answer the question like, what is the experience of GitHub.com for my employees in the London office? So pretty vague, but we can kind of dive into what this means. So from our point of view, we require two pieces of information from our customer. Firstly is a URL for the application that they're interested in monitoring, in this case, GitHub.com. And secondly, the agents that are applicable for this test, in which case the agents in the London office. This is configured in our platform through a web interface. And when this is done, our endpoint agents will begin collecting various metrics. So for example, the endpoint agent will send an HTTP request to GitHub.com to kind of measure high-level response times and status codes and that kind of thing. Or it'll perform a path trace to figure out how the data moves through the internet. And it collects all this data and it sends it to our backend. And it allows us to draw pretty graphs and charts that look like this. So for example, on the top half of the screen, it's a timeline of the latency to GitHub.com. And so what the agent's actually doing is it's poking GitHub.com every 5 minutes, and we're able to plot this timeline of the latency and how it changes over time. At the bottom of the screen, there's a path trace, so it's how my agent's request is going to GitHub.com and all the intermediate nodes in the internet that it goes through before it hits the load balancer at the end. So this is the kind of data and the world that we're working with. But to summarize, scheduled tests work in the following way. Firstly, we configure a test on the web interface. And secondly, the endpoint agents run the test and collect the metrics. Now, from a backend point of view, aside from like persisting the configuration of the test and collecting the metrics from the endpoint agent, most of the work on the backend becomes figuring out which agents need to run which tests. And this is where kind of the reactive programming stuff comes in. So let's take a look at how we're able to do this. I first want to explain some of the interactions between the endpoint agent and the backend. And one of the most important things that the endpoint agent needs to do is check in with the backend. And what this means is that the endpoint agent will periodically poke an endpoint in the backend and say, hey, I'm currently connected to the TransferWise network, or my current location is in London. And you can kind of think of this like a heartbeat. It's effectively the agent submitting its most recent state to our backend. And it's also what allows us to filter out these agents later. So recall on the slide previously, we want to target all the agents in London. And this is how we're able to begin targeting that, because the agent will submit its location. Now, from a backend point of view, this is what happens when a check-in happens. We first put the payload into an asynchronous event queue. We then have a microservice, which we call the scheduler, which listens to this asynchronous event queue. It figures out which tests this agent actually needs to run, and then stores this as state somewhere. And then finally, the agent polls the scheduler every 10 minutes for the test that it needs to run. So every 10 minutes, it pokes the scheduler, hey, what do I need to run? And the scheduler gives him the answer. So that's how it works at the moment. Now, we use Kafka as our implementation of the asynchronous event queue. And specifically in the Kafka ecosystem, there's a library called Kafka Streams, which allows us to do effectively reactive programming on the data in a Kafka topic. And a topic is basically like a channel where the message is published. So for example, in our case, we have a topic called check-ins. Or if you're an e-commerce app, you might have a topic called orders or payments. But effectively, Kafka Streams is a library that lets us do reactive programming within our applications. So let's look at some of the code and see how this looks like inside the scheduler. So I'm a little bit nervous to show Kafka Streams code because we have TransferWise people, and apparently you guys use Kafka Streams as well. So if I get anything wrong, don't shout at me. So what we want to do first is start off with the Streams builder, which is effectively our entry point into the Kafka Streams library. It allows you to set up like various pieces of configuration, but for the purposes of this, just think of it as like the entry point. And what we want to do is start off with the stream method. This returns an object called a KStream, and it basically tells the application to start listening to the Kafka topic called check-ins. The API of the KStream object that is exposed, it's very similar to like the RxJava observable or like the Flux reactor or even like the Java 8 stream for that matter. So it's like kind of generic stream processing API that you get to use. So it has stuff like map, group by, reduce, etc. But what we want to do first is perform a left join with the tests that our customers have configured. So the way a left join works is you can kind of think of it like a database left join. You first supply effectively the foreign table, in which case it's this test configurations global table bit. The second thing you want to supply is the foreign key, in which case it's the customer ID on the check-in. And finally, we output the result of the join, in which case we just want to do a pair of the check-in and the test configurations. The interesting part here is this part, the test configurations. Effectively, the test configurations is also an event or a topic on Kafka. And what this global table method does is it pulls all the data from that topic and keeps a local cache within the service itself. And this is what allows us to do this left join. The cache itself is keyed on the customer ID, which is the same foreign key that we're joining on. And so that's how we're able to join the two pieces of information together. If you've looked at stuff like RxJava or like Reactive before, and you're familiar with marble diagrams, this is the one for the join operator. If this is intuitive to you, I'm very jealous, but yeah, here you go. But going back to the code, the output is a pair where the first value is a check-in and the second value is a list of test configurations. After that, we want to do a map operator. And map is basically the same as any other map operator that you've seen in any other programming languages. It takes an input value and it turns it into an output value. And in our case, we call this assign method on the results. And what the assign method does is it looks at the tests that are in this customer's account, applies the filters to the check-in and see which ones match, and then output the list of tests that match this check-in. Finally, for each test that this agent needs to run, we save it, and then we also publish it to Kafka. And so because we've saved it as state, when the agent polls the scheduler for what test do I need to run every 10 minutes, the scheduler has the answer already. Now, like a natural question to ask is why are we publishing the set of assigned tests to Kafka as well? Well, it's because we want to be able to react on this event later. Because it's still not very good that the agent needs to poll the scheduler every 10 minutes to be able to get the latest tests. For a few things, it's definitely a very bad user experience, because when a customer defines a new test in our platform, they have to wait at least 10 minutes before the metrics start coming in. And that's confusing, and two, that's just not a very good user experience. So we want to get to a state where the agent doesn't actually need to do this 10-minute polling. And this is where we kind of introduce WebSockets to help solve this, right? So just a super brief introduction into what WebSockets are. It's basically a communication protocol that allows two-way communication between a client and a server. So it allows client to send messages to server, and allows the server to send push messages to the client as well. If you kind of compare this with the traditional HTTP approach, only the client is allowed to send a message to the server, and the server has to reply based on a request from the client. So kind of how does this work for us, right? So the obvious use case is for our backend to proactively push messages along the WebSocket connection to the agent when it sees that it needs to assign a new test. So at the first round, my agent might just have a test to github.com, and then a user might configure a test to Google Mail, in which case the backend should just push that along the WebSocket connection without requiring the agent to poll our backend again. So how do we actually make this work? Currently, the scheduling only happens when an agent checks in with our backend. So the scheduler only runs as a result of a check-in. It doesn't run as a result of anything else. And the scheduler doesn't know when the test configuration changes. But the test configuration changes are already events on Kafka, right? So this is what allowed us to do the whole left join thing we saw a couple slides back. So then we're able to listen to these set of test configuration changes as well, since it's already on Kafka. So we introduced another service to react to test configuration changes, which we've called the reconciler. And the name will be a little bit clearer later on. But of course, no surprises, the reconciler is also implemented in Kafka streams. What it does here is first, it listens to the stream of check-ins. So same as before, we start with this builder, and then we call stream, and the application begins listening to this event on Kafka. We filter based on time, because we only care about check-ins that are effectively active. If an agent hasn't contacted the backend within the last hour, we basically don't care about scheduling tasks on them, because they're probably offline if they haven't contacted us in the last hour. So we filter these out. And again, the filter operator here, very similar to filter operators you've seen in other places, like in the Java stream or like JavaScript arrays. What we want to do next is we group them by the customer's account identifier. And so this allows us to process the set of check-ins that are specific for a given customer. And finally, we perform an aggregation over this list of check-ins. And what aggregate does is it's kind of similar to methods like reduce and collect. It takes your stream of stuff and applies some kind of meaningful combination to it and outputs the result of that combination. So in Kafka streams specifically, the aggregate operator takes 3 arguments. The first one is a lambda that sets up your aggregation container. In this case, it's just a list for us. The next argument is also a lambda that defines how you merge each event into the aggregation container. So for example, in this case, we're just adding the check-in into the list, and then we're just returning the list itself. The good thing about Kafka streams is that the result of this aggregation is accessible in a subsequent step. So it effectively stores the result of this aggregation as a cache on your service. And this is what the last kind of parameter is for. You basically give to Kafka streams an identifier for this cache so that you can access it at a later step. And this will become clearer later. So as you can see, the aggregate method is very similar to stuff like reduce and collect. The next thing the reconciler needs to do is actually listen to the stream of test configurations, because ultimately that's what we want to react on, right? So again, we have another kind of stream, where this time, instead of listening to the check-ins, we listen to the test configurations. We do another join, and here is where the cache from before is relevant. Because we created a cache called active check-ins, we can access it again in the join. This time, we're again joining on the customer's account ID, because the cache is keyed on the customer's identifier. And finally, we just output the stuff that was in the cache that we found. So this returns a stream of a list. And so we flat map over that. And what flat map does is, if you have a stream of a list of stuff, then it just flattens it out to give you a stream of stuff. It's one of those operators that's like a bit hard to get your head around at first, but it's effectively identical to the Java 8.1 and all the other ones that are out there. Once you get your head around it, it's actually pretty simple. And finally, once we have the individual check-ins themselves, we just play it back to the same Kafka topic that the scheduler is listening to. So then, how has this actually affected our architecture as a whole, right? We have the scheduler, which is still listening to check-ins, and it's returning test assignments for each check-in. But now we also have the reconciler that listens to test configuration changes. It keeps a cache of the active check-ins, and when a test configuration change occurs, it replays this information back to the scheduler. So that means whenever a test configuration has changed, the scheduler knows about it immediately, because it's listening to the check-ins, and we're replaying those check-ins. This also means that our backend is now able to schedule tests for agents when a test has been modified, and it doesn't require the agent to poll the backend anymore. But that's not enough, right? We still need to have a mechanism of pushing these messages to the agent itself. And so for that, we introduce 2 more microservices. We have a component called the publisher and the WebSocket Server itself. The publisher is pretty simple. I'm going to go through this really quickly. It's another Kafka Streams application, surprise, surprise. This time, it's listening to the test assignments, which, if you recall, is the output of the scheduler. It then enriches it with some metadata. And then for each enriched test, it pushes it to a Redis topic. Now, Redis topics are kind of different from Kafka topics in that they're fire and forget. So if no one is listening to a Redis topic, the message just disappears. But the good thing about that is they're super lightweight and pretty easy to scale and manage. And then we have the WebSocket server. Now, the obvious thing that it needs to do is manage the WebSocket connection with our agents. Now, the WebSocket spec doesn't actually define any sort of application level protocol between your client and the server. All it cares about is this is how you set up a pipe, this is how you set up the connection, and what you send along the pipe is kind of irrelevant to the WebSocket spec. But so it's usually a good idea to define an application level protocol for the stuff that you're allowed to send and receive along the WebSocket connection. And so for this, we use Stomp. Maybe some of you guys have heard of Stomp, but it's just a protocol that defines what the WebSocket connection, what messages are allowed to go through the WebSocket connection. It's a protocol that's been around for a while now. It's pretty simple to understand, and it kind of just works, so that's why we chose it. The idea with Stomp is that each client tells the server what kinds of messages it wants to listen on, or what kind of messages it wants to subscribe to. And then the server sends the relevant messages to the client based on their subscription. So in our case, we have our own WebSocket server, and the client is obviously the agent that's living on the employee's laptop. So what we do first is we open the WebSocket connection, and the connection established. And then the agent says, hey, I want to subscribe to the test assignments that are relevant to me. And the WebSocket server says, hey, good job, you're subscribed. When this happens, the WebSocket server will subscribe to Redis. And the topic on Redis is specific to the given agent themselves. So only the agent's test assignments are coming out of this Redis topic. When the publisher pushes an assignment on this Redis topic, the WebSocket server hears about it. And finally, it forwards this message along to the endpoint agent. So this is kind of our architecture with the WebSocket server. But if we put this all together, this is how it kind of looks like. We still have the scheduler, which is listening to check-ins, and it publishes test assignments back to Kafka. we have the reconciler, which keeps a cache of the active check-ins. And when it hears about a test configuration change, it publishes these active check-ins back to Kafka again so that the scheduler can listen to it. And once the scheduler sees some check-ins, it will generate new test assignments that are relevant for this agent. We have the publisher, which is listening to the test assignments topic, which is the result of the scheduler, and enriches it with some metadata, and then it pushes it to Redis. Finally, we have the WebSocket server that's listening to the Redis topic, and it forwards this message along to the endpoint agent. So that was like a super intense session of like how we've managed to schedule all this stuff. What impact has it actually made, right? This is a couple months of engineering work, and if we have nothing to show for it, it's kind of not very good. Now, when using the polling approach, it would take at least 10 minutes for a new configuration to be published to the agent, because that's just how the polling interval, right? But with this WebSocket approach, we managed to minimize the time it takes for a test assignment to reach the agent from 10 minutes to 10 seconds, because we push it to the agent immediately once it's there. So that's a great improvement. But of course, this also means a much better user experience, because now when a customer configures a new test in our web application, they see the results pretty much immediately or within like a couple minutes. And that's a great thing for us. It's a lot less confusing for the user, and it's just overall better. It opens the doors for a lot of new features as well. In the next couple of months, we're going to add like a Run Now button to a test. And effectively, what we want that to do is push the test configuration to the agent immediately so the agent can start collecting metrics straight away. And effectively, the goal is to kind of have metrics show up within like a minute or less than that. And this is good for us because it addresses like an ad hoc troubleshooting use case that a lot of our customers have. And so not only is like it's a performance improvement, but it also kind of lets us implement new and better customer features. And for this, we plan to leverage a lot of the existing components that we've already built. But of course, not everything is easy and not everything is rosy. Building a reactive system is difficult, and it's super easy to like introduce bugs. In traditional systems where your data is stored in a database, if you have a bug, it's usually pretty easy to just like look into your database and figure out what's wrong. Like if the row has the wrong value, then you can usually pinpoint where your bug is. But in an event-driven system, you don't really have like a database. It's quite hard to look inside your event log and just try and see where the problem was. So bugs are pretty hard to solve. And the way we've kind of addressed that is just through good monitoring and good operational excellence in general. Through our monitoring, we've kind of actually uncovered a lot of issues that we didn't initially realize. And another thing for this kind of like reactive architecture to work, having like a push-based mechanism in the middle usually is the last piece of the puzzle. So for us, the push-based mechanism is the WebSocket server. But that was almost the easiest part of this whole thing. The harder part was more to model everything as an event, so that eventually when the WebSocket server does get introduced, it has that event already and is able to push it along. So modeling everything as an event, you kind of have to flip your way about how you think about problems, and it sometimes makes simple problems pretty difficult to solve. Of course, if everything is asynchronous, then timing also matters. We kind of had a few weird issues where caches were being populated in a downstream or in an upstream service, but the thing downstream wasn't warming up its cache quickly enough. So when a message got pushed through, the right thing didn't happen because the cache on the downstream server wasn't like warm, and so it didn't produce the right result. So again, kind of like with asynchronous systems in general, timing is a big factor, and for us, again, it was down to monitoring and good operational excellence that like allowed us to figure out what the problems were. And finally, writing a WebSocket server in Java is not that straightforward. A lot of the things you see online is about writing chat applications, which we're obviously not. And like a lot of the literature out there doesn't really help. It kind of usually talks about writing single instance applications, where for us, you want to run multiple replicas. And so like a lot of the frameworks that are there as well don't really help. A lot of the time, we had to kind of dive into the framework code and look at the libraries and debug the libraries themselves to actually figure things out. But kind of these were the key takeaways for us. Ultimately, it was a great engineering challenge to solve. And I really think that by embracing a reactive architecture, we brought a lot of value to our customers. Now, before I conclude, I just want to say thanks to TransferWise and JVM Roundabout for having me. I'll be hanging around later as well, so if you have questions or you want to chat, feel free to come along. But otherwise, I hope tonight I've given you a good overview of how we run our systems, the types of challenges that reactive programming brings, and some inspiration for how to make your systems more reactive and event-driven. Thanks.
Cheers, couple. First, why did you introduce Redis PubSub in the middle rather than for the publisher rather than
listen to Kafka straight away? Yeah. So it's kind of going into the weeds of how Kafka actually works. So the way Kafka sends messages to your listeners, it's based on like a partition key. So effectively, each message has a key. And that key lives on a particular partition on a node on Kafka. And when you have subscribers listening to Kafka, each replica of the subscriber only gets one message from a given partition key. So there's no guarantee that the agent subscribing to the WebSocket server is listening to the same partition that its message is coming out of. So we put Redis in the middle to kind of get around that.
Okay. And how do you handle multiple instances of the WebSocket server?
Sure, yeah. So when the endpoint agent first connects to the WebSocket server, it'll say, hey, I want to subscribe to my test assignments. And when it does that, the WebSocket server then subscribes to the corresponding Redis topic. So the Redis topic itself is like keyed on the agent's identifier. So only the messages for that agent are being pushed to that Redis topic. And so like once that subscription to Redis is set up, then the WebSocket server is only getting messages for the agents that it has a WebSocket connection to.
It's, by the way, great presentation. Congratulations on your first meetup. You said that in the beginning. I was just wondering more like the way the business rules of this application work. So when the test assignments get regenerated because the configuration changed, you do not provide any kind of functionality to cancel those that have been already emitted. So like they all will be pushed into the agents.
Yeah, exactly. Yeah. So the kind of like I guess logic that we have on the agent is that it's effectively idempotent. So if you push like the same thing twice, or like it always just holds on to the like latest state. So the actual message that we push isn't like new assignments. It's here are all the assignments that you need every single time. So it's always idempotent effectively.
Yeah, right. So there is no preference between.
Yeah.
Thank you very much.
Could you please tell something about fault tolerance of those pipelines that you showed in the beginning? K-stream pipelines.
Is there a specific?
What if consumer crashes and there were messages in the middle of those pipelines?
Yeah, so the pipelines, because it's on Kafka, it's persisted. So when the application spins back up, it just kind of starts from the position before it crashed, I guess. So it like replays the message, and then we have kind of monitoring around stuff like consumer lag. So basically, how far behind is an application from the latest part of the Kafka topic? So then we get alerted for these kind of things. So like we kind of jump in manually to figure out what's wrong. Good.
All right, thank you very much.